another relatively short video. Basically, hazardous locations, and per the Canadian Electrical Code, hazardous locations are divided into classes. Class 1, flammable gases or vapors, which may be present. And that basically is what we're dealing with the concern of wastewater, primarily methane that can be generated by the stuff in the wastewater. Class 2, you're dealing with dusts, which is not a concern of us, or is Class 3, where you're dealing with fibers. Now, beyond the classes, we then go to zones. And zone 0, you can see, is continuously hazardous. For example, I guess an underground chamber where you had wastewater and no ventilation whatsoever. Zone 1, explosive atmospheres may likely occur in normal operation, or it's adjacent to a zone 0 from which the gases can transfer over. That's probably somewhat analogous to a wet well with natural ventilation, but no forced ventilation. Zone 2, again, class 1 locations where it's not likely to have a explosive gas atmospheres normally, and if they do, it'll only last for a short time, or it's adjacent to a class 1 zone 1 location, which the explosive gas are prevented from being communicated by means of positive pressure ventilation. Okay, that's what you're normally targeting with a pump station wet well, is to be class 1 zone 2. Now, just as a little footnote here, at one time in British Columbia we dealt with divisions, and as you can see, division 1 was split into zone 1, which is probably comparable, and then for really continuous hazards, zone 0. Division 2 is now become zone 2. Then we take a look at the gases and vapors, which are broken into group C, B, and A. Now, group C, acetylene, another similar gas. Acetylene is, we'll get into that later, very subject to being ignited. There's a reason they use it for welding and cutting, because you look at it and it'll ignite. Not quite that bad, but almost. 2B is not to be. Hydrogen sulfide and similar hazards. Group A, methane and gasoline, whatever. That's where most sewage wet wells are. Now, group 2, without the letter, it's all gases included. So just a total hazard rate across the board. Canadian Electrical Code adapted IEC, but also recommends the American National Electrical Code designations, which were previously used under the Canadian Electrical Code. We do try to stay in touch with the Americans. Okay, in step. Now, the division groups that we have, and you'll see in the States, versus the IEC groups. Okay, group A, B, and C. Group A and B basically is group 2C under IEC. Group C now group 2B, and group D, group 11A. That's danger. Now, group C is the most severe system gas group. Hazards in this group can be ignited very easily. Equipment suitable for group 2C is also suitable for B and A, because C is the most dangerous, shall we say, of the bunch. Equipment marked suitable for B is also suitable for A, but not for C. You can always work backwards, but not forwards. If equipment is marked, for example, and this is again European IEC, you can see what it is, then that is suitable for all subgroups A, B, and C. Most municipal pump stations are inherently class 1 and involve the potential of group A and B gases, or potential spills of chemicals and whatever. That can happen. Ruptured gasoline tank and it gets into the sewer system. And under NFPA 20, it recommends, I'm recommending that be checked into. Take a look at it. NFPA standard, which includes the National Electrical Code, which is the basis for a lot of the Canadian Electrical Code. Also given Section 22 locations. which corrosive liquids, vapors, or excess moisture are likely to be present. What that is really saying is not only should you worry about the issue of explosive vapors and whatever, but corrosive liquids and vapors. Uh, these regulations tend to be written around that specific hazard only, and it's sometimes rather difficult to resolve all requirements. In other words, you have to, in some cases, meet hazardous locations from an explosive point of view, along with corrosive and vapors and all that good stuff. Now, moving right along, before a fire or explosion can occur, three conditions must be met simultaneously. You need a fuel, a combustible gas, oxygen, air, and they have to be at the right proportions, and then a spark or flame. That rate proportions will come to in a minute. The ratio of fuel and oxygen that is required varies with each combustible gas or vapor. The minimum concentration of a particular combustible gas or vapor is defined as the lower explosive limit. In other words, you have to have a certain amount of that hazardous gas to get it to explode. If you're below it, if the concentration of that gas is below and mixed with air is below that limit, it will not ignite. It's too lean. If you get above the upper explosive limit, it's too rich. So there's that band between the two where the flammable range for that gas or vapor exists. And here is an interesting little chart to take a look at. You notice with acetylene, and these are in percentages, acetylene, the lower explosive limit is 2.5%. The upper explosive limit is 100%. In other words, you cannot get it too rich to not ignite. So virtually an extremely broad range. By comparison, if we take a look at methane, its explosive limit at the bottom end is 5%. Anything leaner than that, it won't go. And anything above 15% is too rich. So you can see there's quite a wild range. Similar to gasoline, for example, between 1.2 and 7.1 is the ratio of air and gas that becomes a explosive ignition concern. Now, several means of providing protection within a zone, but the two most common are either intrinsically safe or, we'll get to in a minute, fireproof, flameproof. Intrinsically safe, what that means is anything in that area that is liable to cause a spark, the spark will not have enough energy to actually ignite it, okay? And the classic definition of that is 24 volt at a maximum of 100 milliamp. And if you look at the chart on the right, basically anything, and you got the lines for like methane, propane, ethylene, hydrogen, the different groups. And you see the star, that is 24 volt at 100 milliamp. Anything below that line, there is not enough energy, not enough spark to ignite it. Anything above the line of the group you're concerned with, it will ignite it. So how they do that, this is primarily control only. So what you end up doing is have, starting at the right of that little sketch, you've got your control equipment room. We're talking control, not power. And for control stuff, we have an intrinsically safe barrier, which basically is a relay that allow you to operate at or below 24 volt at 100 milliamp, and at that low power, then you can have intrinsically safe equipment inside. Still has to be approved, but it's pretty simple because there's nothing really exotic happening there. Now, the other way of doing it, which is perhaps the more classic way, is flame proof, basically called explosion proof. And what it is, you have an enclosure that can withstand an internal explosion of the gas without it igniting the gas that is beyond the enclosure within the room. So how they normally do that is basically, you can see there's a million bolts so the thing isn't blowing apart, but gas can squeeze through, no gasket. Basically the gas can stream through, and in doing so is cooled so that that gas jetting out will not ignite what's in the room. So there's a small explosion in the enclosure, and then this enclosure allows you to prevent a major explosion beyond that. Okay, I mention here, if sealing is desired, you can get some enclosures that use an O-ring and a groove. You still have a lot of metal to metal to cool a gas, and you have an O-ring that will seal out liquids. And to be honest, if there's an internal explosion, goodbye O-ring. Testing. This is how CSA does it. It's kind of interesting. They will take a gas within a group, and the most ignitable gas will be, here's the enclosure, will be put inside a bag, and the bag filled with the most ignitable gas. The enclosure will have been filled with the most powerful gas within the desired group. Then they have a spark plug device attached to within the enclosure that they've added. When they trigger the spark, the question is, will the bag blow up or not? If it works properly, the gases will, there'll be an explosion within that enclosure. They will shoot out, but going across that metal to metal contact, they will be cooled enough that the gases in the bag do not ignite, and therefore the bag doesn't explode. If the gas is coming out, and you see the little pink arrow on the drawing to the right, if gases do come out and they're hot enough to ignite, then the bag gases will go off. Boom, that's it, and it's considered that the test was a failure. Now, how do you isolate zones? The classic way of doing it is using what they call EYS seals. And the Y is because it's sort of the shape of the thing. And like conduits and everything else, if you're going into an area, basically how they seal that is by putting in a compound that fibers to kind of create a dam between the conduit coming in and the conduit going out. And in between, they'll fill it with an epoxy sealing compound that's poured in. Can make the interesting thing about that seal pretty much prevents you from ever pulling those wires out in the future. So what you ideally want to do is have that, and then above it an enclosure so that you can service anything beyond it, or even on the other side. Okay, so junction boxes on both sides of that seal are a good idea. Here it shows here without the junction boxes, but there's the EYS seal with the red arrow, and it is sealing everything above from what's below. So where that red arrow is, either above or below the EYS seal, usually below is where you'd go from, say, the control room to that 100-horse pump in a hazardous location, like a submersible in a wet well, and the seal is preventing gases from going. Basically, the seal has to be within a conduit length of the wet well. Okay? But conduit is not the only way of doing it. You actually can get seals specifically designed for tech cable that works exactly the same concept, except they have, you see in this drawing, mechanically, they actually have an integral sealing compound. And again, the concept of gases escaping along the threads and being cooled off, so that if there's an explosion within that junction box, it will not travel and ignite the whole room. Okay? Often used approach of wastewater pumping stations is to take advantage of continuous wet well forced ventilation, which, number one, reduces your classification down to 2 if you've done it right, class 1 zone 2 environment. But it also reduces odors and generally makes for a better environment. Okay? And at one time, you could, class 1 zone 2, conventional motors were acceptable to that as long as they did not incorporate arcing, sparking, or heat producing components. And believe it or not, a standard open drip proof motor met that requirement. Now, it depends on the electrical code for wherever you are. Some is insisting you have explosion proof motors, and we'll get into motors in a bit. You may find that they still exist. I think this is a good approach, but different people, different strokes. The ventilation air was classically sourced from the sealed kiosk compartment with seals going through an EYS that contained a fan that was monitored by a remote kiosk-mounted differential pressure switch. In other words, they basically wanted to know that an alarm would be fired if the ventilation system failed. And you can get these devices that operate on very low pressure, and you can mount it in a kiosk, and literally the sensing differential on the one side is the kiosk air, on the other side is you sense it to where the chamber is actually, the kiosk chamber is actually being vented, and that little difference, which is very, very slight, is enough to trip the switch. And if you've got normally closed contact, fine. And when it fails, the contact will close. Boom, you've got your alarm. And again, changes to electrical code driven by electricians and electrical inspectors, and electrical inspection is the authority having jurisdiction, are ongoing, as are provincial and I'm sure state amendments. The authority having jurisdiction will ultimately have the final decision and should be consulted for guidance if uncertain. They are gods. Most of them are very nice gods, but they are gods. Okay, that is it for hazardous locations, and do hope you enjoyed.